Which one do you want to talk about? Let's have hands here. Which one do you want to talk about? Yeah, which one? No, no, bad answer.
Number 5.
Bad answer. We get to pick one. Which one do you want to do? Number 5?
Or 9.
5 and 9.
5 and 9. So we have a bid for 5. This one right here. Ball is thrown. That question.
Yes.
Okay, let's think about this. So it says a ball is thrown into the air with a velocity of 40 feet per second. Its height in feet after t seconds. So is this a velocity function?
Yes.
No.
No.
Its height after t seconds. Is this a velocity function?
No.
No. What is it?
Height.
So we're not calling it. Yeah, it's a height function, but in physics term, you wouldn't really call it a height function. What would you call it? Yeah, position. Free fall. It's going up. It's going down, right? So we'll call this time. Do you usually have all the quadrants like that? No. Well, not uneven, but do you usually draw all 4 quadrants when we're talking about a question like this?
No.
No.
Usually
Time is positive, right? Generally. I mean, well, no. I mean, hopefully in real, but there are times when you want to, like, if you're starting in the middle of something, your index time might be in the middle, and you might want to move backwards or forwards. But in this case, time is 0. At time 0, how high is this thing? 0. What's another point if you wanted to graph this by hand that would be helpful to have?
216.
Well, hold on.
Oh.
If you're going to graph a parabola, which is what this is, you might want to find the vertex, but also the what?
0.
The other 0 if it has one, which this one will. Does this parabola face up or down?
Down.
Why? How do we know that?
Because it's negative.
What's negative?
The coefficient of the squared.
Yeah, the coefficient of what would be the leading coefficient if we wrote this in the proper order. How would you go about finding the intercepts really easily? What would you do first?
Factor.
Yeah, factor, 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 factor. I love factoring. So if you do that, you know one of them is 0, but what's the other one going to be? Well, you know that 10 minus 4t has to be 0, so you know 4t is going to be 10, so t is 5 over 2. Do you agree with that?
Yeah.
We'll just call that 5 over 2. And this thing goes up and then it goes down. And we're assuming it can't go below the ground, so let's just draw this parabola. Yay, like that. Do I really care about scale?
No. Nope.
Not really. I don't really care about scale too much on this. Okay, we don't know if this will be helpful, but now we have a picture. It helps us think about it. Find the average velocity for the time period beginning when t equals 2 and lasting 0.5 seconds, 0.1 seconds, 0.05 seconds, and 0.01 seconds. So, what's an easy way to find the x-coordinate of the vertex? Someone raise their hand and tell me. What's an easy way to find the x-coordinate of the vertex if you have these 2 intercepts? What's the easiest way possible? What can you tell me about the shape of a What can you tell me about the shape of a parabola? It is symmetric. It's symmetric, right? So where does the vertex have to be? In between any 2 coordinates that have the same y value. We have 2 coordinates with the same y value. We have the x-intercepts. So what's the x-coordinate here? 5 over 4. Right there. Exactly. 5 over 4. So for the time period beginning at time equals 2, where is time equal to? Well, it's somewhere around here, right?
Yeah.
There's time equals 2 right there. So let me blow this up a little bit. Let me make this a little bigger. So what are we now looking at? We're really looking at, so here is this section right here. And let's just say time equals 2 right here. I'll make, that's fine. So we want the time interval, the average rate, the average what? The average velocity? The average velocity for a time interval lasting 0.5 seconds starting at time equals 2. So where does 0.5 seconds end? So t equals 5 over 2. So if you're finding the average velocity and you have the position function, what are you trying to find? You're trying to find the slope of the secant line. You want to find this slope, right?
Yes.
Here. Not very nicely drawn. So in order to find the slope between 2 points, you need to actually find the... Yes, to find the slope, you need to find the slope. To find the slope between 2 points, you need to actually find the...
2 points.
You need to find the 2 points. The first one is 2 comma something. The other one is 5 over 2 comma something. What's going to go right there?
You know it's 0.
You know that one is 0. Yes, you know that one is 0, but this one's 2. You know it's going to be 40 times 2 minus what?
16, 2 squared.
Squared, right? So that's going to be 80 minus what? 64, which is? 16. So what's the slope between those 2 points? It goes what's the vertical change? It goes down what? And it goes over what?
1/2.
1/2. So what's the slope going to be?
8.
Nope. Negative 32. Dividing by half is multiplying by 2.
You're right. I know.
So
I'm wrong.
we just found our first one. So what are the units on this? Meters per second. Yes. And it should it be negative? Yeah, it's going down.
Is it meters per second in this one, or is it feet?
Is it feet?
I think it's feet.
Is it? Oh, it is
Yeah,
feet.
yeah,
Yeah, it is feet. Thank you. It's fine. It's totally fine if you default to meters per second. That's totally okay with me.
Make the
The
law
worst
more
questions we're gonna do are the ones where they're like, okay, I'm gonna give you liters per teaspoon, and like you're like, I don't know what that is. Help. Foot pounds per. Yeah. Yikes. Okay, so that's one. So we have to do the same exact thing, but now we're doing it for a time interval of 0.1, 0.05, and 0.01. Now here's the thing. Could you do it the same exact way every time?
Yes.
You could. It gets monotonous, right?
Yes.
It might be helpful to do what?
Try to find an equation.
Write an equation, right? For example, this is for 4 points. What happens if I asked you for 100 points? Would you do 100 of these time intervals by hand?
No.
No, you wouldn't. So let's see if we can set this up on the calculator. Okay, so what was that equation we were typing in? 40 times 2 plus a. So instead of a, what are we going to do? We're just going to call it what?
X.
Oh, what mode am I in right now? Anybody know?
No idea.
No.
No, but look at the functions. It's beyond that. I was in polar right there. And also, let's put it back into radians. Ooh, it really doesn't like that, does it? Wow. Button got stuck. That's fun. So go back to mode. Change it back to radian. Kind of important. Not really on this one, but important in general. So I'm going to clear this to go back to the nice graphing that we know, right? So what was it? It was 40 times what? X plus, well, 2 plus x. Does it really matter if I do 2 plus x? Or, yeah. Divided by what?
X.
Divided by x.
Minus.
And then we subtract what? What was it?
Yeah, you
Now, hold on. Do I need parentheses?
No, because it's a division function.
Technically, you would think no. But the calculator is really, really, really kind of weird about parentheses. It's kind of annoying, isn't it?
It is.
What am I subtracting? 16 times what? 2 plus x squared, right? Correct? And then what am I dividing it by? Times x, right? And then what's the last one? Minus 16 divided by? X. Are we particularly interested in what the graph looks like? Sure. What do we want to do for a window? Well, the time it's going to go from 0 to, not 5. We were only interested, what was the biggest? 0.5, right?
5 halves.
over 2. Yeah.
What?
5 halves.
Yeah, but this is in terms of the gap.
Oh.
We wrote this in terms of the gap. We didn't write this in terms of the x value. So we want to go from 0 to, let's go to 0.75. Let's go a little bit further. Okay? The y minimum,
0.
what do we want to call it? We know it's going to be negative, right? We'll go from 0 to what?
Negative.
Well, actually, the y max is going to be 0. What's the y minimum going to be?
Oh, right.
The y minimum is going to be 0, and the y maximum is going to be... Sorry, the y minimum is going to be negative. It's negative, right?
Negative.
What should I make it? Negative what? 10. Okay, so let's graph this. What does it look like? Are we guaranteed to see anything?
No.
Hopefully. Yeah, what do I press?
Second graph.
Second graph. Okay, so that's not super helpful, right? So I need to change some of this. What should I do? These values aren't particularly helpful. Well, why?
You should put it on insert or
Table set. Anybody see table set right there?
Yeah.
Second table set. Where do we want to start the table? Where do you want to start it? What's the starting value? 0.0 or what? 0.0 what? Come on, guys. 0.01? Yeah. Okay, so 0.01. What do we want the step to be? Like how much do we want it to move? Yes, I see that it didn't do that right. 0.01. What do we want we want to change by 0.01? You can do that. That's fine.
Yeah.
So look, it's starting at 0.01 and it's changing. So look at this. So 0.01 does this. Yay. So we needed some of this, some of these values. We could go all the way to, does it match? What would be a good value for us to check, just to see if it matches reality? We checked 0.5, right?
Mm-hmm.
And I'm still clicking. I really got to stop clicking.
Negative 32.
Did it work? Was it the proper
Yeah,
value?
it was.
It was the proper value.
It
So
was.
this right here does match. So that's a good sign, right?
Yes.
So if we go back to this, we go second quit here, and we go to the graph. Second calc, you see value right there? X equals What was one of the other x values we needed?
0.01.
0.01. You hit enter. There it is. So when x is 0.01, we end up with the y value, which in this case is the slope of the secant line. So, does that match what you guys got? Did anybody else do it by hand? Does that match?
Yeah.
No one's shaking their hand. One person? No one's looking. But what's nice about this, can we test other values?
Yeah.
Sure. What would be a nice value for us to test if we're looking for the actual value here? We can go back to the question. The question's asking, so you test all those. Find the instantaneous velocity when t equals 2. They want you to make a table, right? So that was 0.01. So what would be another one for us to check? How about second calc 0.001? Negative 24.016. What would be another value for us to test?
0.1.
We just tried. We want to get closer to the actual value. This is the gap.
0.00.
0001, right? So let's test the limits of this calculator. Second calc value 0.1234. Let's go even further, right? Enter. So do you have a strong suspicion as to the actual?
24.
Do you have a strong suspicion? Yeah. Is that a proof?
No.
No.
No. We strongly suspect
Got a hunch.
that the instantaneous velocity at time equals 2 is negative 24 feet per second. Yes. Shaw. What movie now? Yeah. Okay. So, what do you do now once you have that function?
Plug it in.
Plug it into what?
Y equals.
Yeah. Okay. So y equals, and what was it? It was sine of
10
10
pi
pi
over x
divided by x
minus 1. Oh,
divided by what?
x minus 1.
Did I type that right?
Yes, unless it's gonna
Correct.
make you need more parentheses.
I think it's okay. I think because the sign pretty much pulls everything together there. Okay, so we'll go back to this question. It says we need values from x equals 2 all the way to 0.9. So let's go from, let's set a window
0.5.
to what? No. Oh, 0.5 is, they didn't
Yeah,
do it in
I
order. Oh, that's annoying.
I wanted to order
Okay, so we want it to go from, let's go from 0 to what? I don't know, 2.5. Is that fine?
Yes.
Does it really matter? As long as the domain is there, it doesn't really matter what the range is, generally speaking, because we're really interested in just evaluating this function. If we want to graph this, let's just do, I don't know, quit. We can go to the graph if we want to. The y values are so weird on this one, we're probably not going to see anything, right?
Oh, no.
Oh, look, that's actually kind of cool. Okay, so we don't really care what this looks like. We're looking at about making a table, right? So if we want to table set this, what do we want to start at? We'll start at 0, and let's make it. What's the delta table? How far up do we want to go each step? Can someone get the door? 0.1, right? And now let's go to table. It's giving us an error because when you plug in 0, why is it giving you an error when we plug in 0? That's what I want to think, but what's the equation here? Oh, it's undefined in the numerator. You're dividing by 0 inside the sine function. There we go. Okay.
Madness ensues.
Madness ensues. That's right. Okay, so we have part of the table here. There it is, and let's just do the rest of the table. Down. I gotta learn when not to press anything. Ooh. Okay, so we have this now. So essentially, you're trying to observe what? You're trying to observe a pattern, right?
There is no pattern.
There is no spoon. Okay, this is helpful. Now, what do you notice now? So let's actually get to the second question here. The question now asks, okay, do the slopes appear to be approaching a limit? Do they appear to be approaching anything? 0, 0, 1.23. They keep on bouncing around, positive, negative. Does it look like they approach anything?
No.
It really doesn't look like that. You could answer, no apparent pattern. And you can't be sure, but just, I mean, do we really have any big tools to use yet?
No.
No. I mean, you're looking at it and going, no, it doesn't look like there's a pattern. Use a graph of the curve to explain why the slopes of the secant lines are not close to the slopes of the tangent line at P. So if we looked at P, it's 1, 0. We could look at the values around 1. We could get really close to 1. Now, is that close to 1 right there? Is 0.1? Close is a totally relative term. Is 0.1 going to be close enough here?
No.
No, because there's a big error. It doesn't, so we could, if we wanted to, right? We could change the table set. Let's start at, I don't know, 0.99. Let's make the step 0.001. Does this make sense, everybody?
Yeah.
When we do the table now, look at the table right now. There's an error there, right? But does it look like from both the left and right side, are they both approaching this around the same value?
Yeah.
Around 1, it looks like the slope is like around what?
31.5.
Negative 31 point... No, it's between these two, right? So
Right.
0.441, right? It looks like, that's our guess, right? But if we look at this right here, it's bouncing all over the place. The initial path doesn't look very smooth. Do you agree with that? It's going all over the place? Okay, so the question then asks, use a graph of the curve. So let's take a look at this graph here. We need to change the window. Let's go from, I don't know, let's go from negative, let's go zoom, how about this, zoom trig. What's it look like's happening around the origin?
Insanity.
Or actually around 1, around the point P. Insanity, right? Looks like it's pretty crazy. Now, let's look at the function again. You're doing sine of 10 pi divided by x, right?
Yes.
Where do you want to zoom in here on this graph?
On 1.
Where x equals 1?
Yeah.
So let's do a window. Let's change this to go from, I don't know, 0 to what? 2? Let's graph this thing. Look what's going on.
More madness.
Madness, I say! Madness! Total craziness.
And then it goes normal.
Okay, where's x equals 1 there?
Um,
Way high up, right?
Yeah.
Goes way high up. So what's going on here?
Actually, it actually goes way far down.
Way far down, I mean. Way far down, yeah. So why, if we're looking at values that are too far out, what's going on if we go too far out? The graph is still going berserk, right? So what is this trying to tell you? What lesson is this trying to, it says, by choosing appropriate secant lines, estimate the slope of the tangent line of P. Well, we already kind of did that, right? So when we looked at this, when our step was 0.1, why wasn't that a very good step to use?
Because relative to the function, it wasn't good enough to capture,
A smooth section of the curve. That smooth is a great word to use. If you go too far out, it's going berserk. But if you get close enough can be different things for different functions. So what's the note here? What are you taking out of this question? You may need to get really close. 0.1 might not be good enough. We had to go to 1/1000th to be good enough. Notation. You will see this a whole lot right here. You'll see this a ton. What that means, if you're saying that out loud, you say it as the limit of f of x as x approaches a equals L. That means as the x coordinate gets closer and closer to the value of a,
it will get closer and closer to that.
the output value, f of x, gets closer and closer to L. So let's draw a little picture of this. So what that means is your function's traveling along right here. And here's the a value right here. X equals a right there. So we'll put a nice big point right here. So at this point, what's the y value in terms of this definition?
L.
L, exactly. So as this point travels towards it from either direction, so as x gets closer to a from both sides here, so x is getting closer to a, what's happening to the y value? It's getting closer to L from both directions. That's what that means. That's actually what that means. Okay, so another way to say that is if we can make values of f of x arbitrarily close, if we can make the values of f of x arbitrarily close to L by taking x sufficiently close to a but not equal to a. It means that we can get the value, if L is the limit, we can always get closer to it by taking x values closer and closer to a. So for example, we just talked about close means different things, right? Close could mean 0.1, close could mean 0.01, it could mean 1 million, 1 billionth, right? It means that L is the limit if you can always get closer to it, simply put. Does that make sense?
Uh-huh.
If there's the barrier might be 1 millionth of a unit away, but if there's a barrier, is it a limit?
Uh-uh.
No. For example, if I go halfway to that wall and halfway to that wall and halfway to that wall, can I always get closer to the wall?
Yes.
You can always get closer. But let's say there was an invisible barrier 1 inch away. If I get stopped by that barrier, is the wall the limit anymore?
No.
No. You can always get closer. You're going to see the word. There's a really, really important word here that you can use if you want to. Arbitrary, an arbitrarily close distance, an arbitrarily far, arbitrarily close. You can use both of those phrases. Okay, so that's important. Let's look at some examples. That's the best way to get into this stuff, I think.
How are you figuring asymptotes?
Ah, that's a fantastic question. Some of these are, well, let's just do some examples and let's clarify that, okay? Okay, let's look at the first one here. And actually, I'll take that out. Let's just do the first one. So what's this limit saying right here?
As x approaches 1.
As x goes to 1, what does that function equal? What's the first thing you always check if you're doing a limit? What do you think the first thing is?
To check if you can solve it.
Yes, exactly. You're gonna have a point in this class. We're gonna be doing a limit. You're gonna have all these different tools to attack limits. You're gonna spend 20 minutes on it. You can't figure out, how do I do this? Then you realize, oh, I just need to plug in 1. Just need to evaluate the function. Always check and see if you can evaluate at x equals a. Can you on this one?
No.
No.
Can't plug in 1. So on this one, I give you you can't plug in 1. That's the issue. So what could you do? Can you simplify anything? Always look to do what? Bill, stand up. Always look to do what? Simplify. What's the best way to simplify, or what do I think the best way to simplify it?
Factor.
Always factor. You always, no matter what you're doing in math, it can almost never hurt to try to factor something. So in this case, it's the same as the limit as x goes to 1 of, over what? Times. So what's nice now?
Now you can
You
factor
can
out.
take out the removable discontinuity.
So in this case, this is a removable discontinuity. This is not an asymptote. This is a removable discontinuity. So this thing actually equals this function right here. So this, I'm going to say kind of here. This does equal, it does equal the limit as x goes to 1 of 1 over x plus 1, which is what? 1 over 2. This function right here, f of x equals x minus 1 over x squared minus 1, does not equal, it is not identical to 1 over x plus 1, which we'll call g of x, okay? They're not the same. What's the only difference?
You fill in the hole.
One specific point. All we've done is we've plugged the hole. This is a removable discontinuity right here because we canceled it on the top and the bottom. It's a removable, I love multisyllabic words, removable discontinuity, okay? So what does that mean? When you're traveling along, this function is traveling along, and all of a sudden there is a hole right here. What's the x value of that hole? What's the y value of that hole? 1/2. We just figured it out.
Yeah.
It means that if you filled this hole right here, that point would be 1 comma 1/2. So what's the limit? What can you get infinitely close to?
1/2.
Yeah, a removable discontinuity is by definition going to be something that you can get infinitely close to. If you couldn't get infinitely close to it, what does that mean? Something else is
In the way.
in the way or missing, right?
Mhm.
Meaning it's not there's something else going on. So you've just learned 2 tactics, 2 hugely powerful tactics. What are the 2 things you've learned so far? 1,
Always try to solve it.
evaluate, right? And what's the second thing? Simplify. Yes. Factoring is going to be key. Can you plug it in? Can you simplify? Okay. Those are some good ones. Is that always going to be the solution to everything? Yeah, sure. Yeah. Yeah.
It's probably a question, but when you had 1 over x plus 1, how did you get to the 1/2?
Oh, I plugged in 1.
Oh, you just.
Now you can plug it in.
Oh, that was the point.
That's the whole point of it. Yeah, yeah. Now we can plug it in.
I
So then you
understand
plug it in.
I can guarantee, I'm just warning you right now,
What else?
you're going to get to a point where you're going to be working on a limit, you have no idea what to do, you're going to try all these fancy things I teach you, and then you're going to be like,
So always start with.
always check to see if you can evaluate. 请坐. 谢谢. Okay, so let's take a look at another one here. Let's take a look at another one. Let's see if you like this one.
Probably not.
No, you'll like it. Take a look at this function. What kind of function is this?
These ones.
It is a piecewise function. This one is, hold on, this one, hold on.
Is there supposed
Identical.
to be a limit as x approaches 1?
Yeah.
Oh, yeah, I'm sorry. There
Okay.
sometimes. I had to hand type a lot of this. This should be the limit as x goes to 1, yes. Sorry, and then it says, so we're doing the limit as x goes to 1 of what? G of x. What's the only thing I changed about this function?
You added... You took the hole and you filled it with a point at a different location.
Yes, exactly. So what that means is this function is traveling, right? There's a hole right here. What's the x value?
2.
But we know that the y value here is 1/2. But what did I fill it with? 2, up here, right?
Yeah.
So that right there is 2, 2. If the limit is what you're getting infinitely close to. So imagine you're a bug and you're traveling along this line, like you have this little bug right here. And this guy's traveling this direction right here. Or there's another bug right here, traveling in this direction like this. What height are they getting infinitely close to?
1/2.
Yeah. They are getting infinitely close to 1/2. Is the limit 2 here? No. Can those bugs even see that little point up there?
Nope.
No. Can they get infinitely close to the y value of 1/2? Yeah. So did the limit change here?
No.
No. It still equals 1/2. The limit did not change. Can you get infinitely close vertically to 1/2? Yes. You can get arbitrarily close. Is it the limit? Yes. I'll flip it around. Can you get infinitely close to 2?
No.
No. So is it the limit?
No.
Absolutely not.
So when you see a piecewise, you automatically...
Well, no, it's not. You have to. It's case by case. Weird things can happen. Just be careful with. I can't make a general statement about all piecewise functions because what can piecewise functions do?
They can
Anything.
seem continuous,
They can seem continuous.
and then they'll trick you to think.
Yeah, just be careful. They can do anything you want, essentially. Okay, we're gonna do a few more of these. They get nasty. So this one right here. So on this one, can you simplify it? Is there any factoring you can do?
No.
That equals 1.
Yeah, that equals 1.
Yes, congratulations. Why?
Because Mr.
Calculator.
Grosso told me
Because
so.
Mr. Grosso told me so. Yeah, it does equal 1. Now here's the thing. If we wanted to believe that, as like what could you do? You could,
Prove it?
well, the first thing, without proving, we could get a picture. We tend to believe what we see. So if you graph this, first one here is the limit as x goes to 0 of 1 over x squared. So the big question here is, what happens to this? Homework. Think about that. It looks like, when you do this one, this is what it looks like. Well, let's see what the calculator tells us it is.
It's not bad.
Y equals, well, you'd think it wouldn't be, right? Divided by what? X squared, right? Zoom standard. Let's see what the sucker looks like. Huh. Goes way high, right? It seems like it spikes up. Well, let's look at this. Look at the actual values. When x gets, let's go from the right. So let's take the limit as x goes to 0 from the right. 1 over x squared. X gets really, what's a really small number squared? It gets smaller. What's 1 divided by a really small number?
A really, really, really big number.
Really, really big number, right? So what do we say this actually goes to? It doesn't equal.
Positive infinity.
Yeah, can you get to infinity?
No.
Is infinity a number?
No.
It's an idea, right? In this case, if you go from the left, what happens if x is negative? When you square a negative, what do you get? So in this case, the limit as x goes to x0 from the left of 1 over x squared, what's that equal?
Infinity.
So generally speaking, so what would you say? You would say this equals, depending on the book, some would say equals infinity, some would say an arrow. The other thing is, could it approach infinity at different speeds?
Yeah.
It could. Generally speaking, it's not going to come down to that, but in this case, it would be okay to say it's infinity. What happens? What about this one, though? What's the limit as x goes to 0 of 1 over x? No, so it's not. From the right, it's going to go up, and from the left, it's going to go
Down.
So as you go to 0, it goes to different places, right? That's definitely different, right? So it does not exist. Okay.
So what are we actually